still there. Okay. One. Test 1, 2, 3. And this one. Yes, all right. Yes. We get back to, oh no, you have to share screen, right? I have to share screen right now and yes, test the sound. Test 1, 2, 3. Okay. Yes. Yes. Good afternoon, everyone. Welcome you to SCI33206, which is what is that? It's physics number 5, right? For M604, we have to start on page 16, right? And anyone who would like to join? Is there anyone who would like to join Zoom? มีไหมครับใครต้องการจอยที่ Zoom นะครับเข้าที่ Zoom มีไหมครับ I'm going to check also whether any comment in the line group or not. Okay. yes, we arrive at somehow the what is that? It's page number 16, right? Yes, here is the nuclear force, right? Yes, the heavy nuclei, right, are more stable once you have more neutron, right? If you have more neutron, you would have more attractive force, right? For the bigger nuclei, you would have more protons, and the more protons you have, the more repelling forces, right? You're gonna receive too, right? And in order to reduce the repelling force, you need to have more neutron, because if the nuclei have more neutron, you would get attractive force, and that could reduce the amount of repelling force. All right, and that's the nuclei condition, right? Yeah, but too much neutron will not be also stable, and you're going to see it later in terms of beta decay and beta minus, beta positive decay. alright นะครับมีใครจะเข้าที่ซูมไหมครับเรา605นี่605นี่ตามอยู่นะครับ605ตามมีใครจะเข้าอยู่ไหมครับ There is the Chai is it right รัตนโยธินครับรัฐโยธินครับanyone who want to join the Zoom I'm going to wait for you, but if not, then go ahead with that. Today is 12, right? 13 is the day that you have to deliver the second time of the midterm exam, right? Okay. Yes, the where is that? Let me bring you to the. Okay. Anyway. It's better if I bring you to another monitor so that I can observe what's going on with the right. Okay. All right. And we're gonna check everything. All right. Oh. Okay. Yes. Yeah. You may have seen from the plot of N by Z or Z by N, right? The ratio between the number of protons and neutrons, right? And yeah, usually the nuclei would prefer to have more neutron than the number of protons. Okay. Yeah, neutrons are affected only by the additive nuclear forces, and eventually when Z is equal to 83, which correspond to the bismuth, right? And the repulsive forces between protons cannot be compensated for by the addition of neutrons, and bismuth is not after bismuth, the nucleus will no longer be stable, right? Yes. Yeah. Anyway, this is the Zoom channel, right? Anyone want to join more in Zoom? No, huh? And here is the text by Chaisit. Yes. The nuclear force is a short-range nature, right? Lies in short-range nature, and it interacts only with few nearest neighbor rather than all the nucleons in the nucleus of the neutrons. Okay, the mass of one important thing is the mass of the nucleon, right? Any particle inside the nucleus, and it's called nucleon, right? Nucleon can be either proton or neutron, right? And the mass of masses of these two particles, subatomic particles, as follow. MP, the mass of the proton is around 1.67, okay, 1.6726, okay, which is less than the mass of the neutron, okay, and the order is on the same, negative 27 of 10, right? And the difference is only the third, the number after the third digit from the decimal point, which is now, it starts with 4 for the neutron, but this one for proton, it starts with number 2, okay, the 2 digits in parentheses indicate the uncertainty in the last 2 digits, okay, the same 1 and 28, plus and minus 29, okay, for each value. It depends on the precision of your measurement device at that time. All right, okay, yeah, the next thing is the precise measurement. It is useful to define a new mass unit, okay, because once we want to calculate anything in the atomic scale, the appropriate unit is the atomic mass unit. It's denoted by 1U, and the reference for that is the neutral carbon atom. Okay, neutral carbon atom means that you have complete electron around that, okay, not the ionized version. Okay, yes, the this is the obvious version, right? One atomic mass unit correspond to 1.6605 and blah blah blah. Okay, this is the uncertainty from the measurement, and it's almost the same as the mass of the proton and neutron, right? It's on the same scale, 10 to negative 27 kilogram. Okay, it's not appropriate at all. It's not suitable to talk about the mass on the scale of 10 to negative 27. All right, so it's better once we consider the particle on the atomic scale, we're gonna use 1U, okay, atomic mass unit. The masses of the proton and electron after being converted to the atomic mass unit, okay, AMU is denoted by simply letter U, okay. It's okay, if you can see that 1.67 is very close to 1.66, right? So it's around 1, and this is also around 1. The mass of the proton is around 1, and the mass of the neutron is around 1 atomic mass unit. The mass of the electron is quite far away from, quite smaller than the mass by proton and neutron. It's negative 31, right? So it's 1 by 10,000, right? 1 by 10,000 smaller, 10,000 smaller. So it's going to be somehow 4 digits, okay, after the decimal point. So yeah, you could get somehow 0.00054, okay, and that's the atomic mass unit for proton, neutron, and electron. We can find the energy equivalent of 1 atomic mass unit for the relation EMC²2, and this is very convenient if you want to convert the mass to energy from the Albert-Einstein equation. Okay, EMC². Okay, E is the energy and M is the mass of any object, right? Mass of particle and so on. This relation is valid when you have a very high speed of anything, okay, any amounts, and the mass of the subatomic particle could be converted to the energy from this relation. Okay, and yes, it's, yeah, if you simply put 1 atomic mass unit here, which is this number in the SI scale 16605 or 4, okay, 54538 approximately, And this is the mass of one atomic mass unit. And once you substitute the exact value of the speed of light, okay, the light speed approximately 3 times 10 to 8, right? 2.99. And yeah, you leave them in a calculator, you would get the energy in the SI scale, which is very, very small, 10 to negative 10. 1.48, right? And it's more appropriate if you convert the energy to the electron volt, right? Electron volt is the appropriate scale in the previous chapter, right? Once we consider the rotation or the orbit of the electron, but this in this chapter we are talking about the nucleus or nuclei of so many atoms. So, and as you know, right, the energy from the electron is not much, and the one from the nuclei is much more stronger. It's around 1 million or 10 million stronger. Okay, the energy you could get from nuclear scale is much more than the energy you get from the electron orbit, okay, electron scale. Okay, yeah, we need to convert this energy to electron volt, okay, to be in the same way as the previous chapter, electron orbit scale, and we divide this amount by the electron charge, okay, 1.6 blah 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 times 10 raised to negative 19. You would get the amount of the energy from one atomic mass unit in the new unit, right? It's in electron volts, and the outcome is that it's quite far from electron volt. Is not appropriate because we have so many digits in front of the decimal point. So it's hard to communicate with each other once you have so many digits in front of the decimal point. It's better to scale somehow by dividing this number by 1 million or 10 raised to 6, right? 1 million. So once you divide by 1 million, move the decimal point by 6 positions, you get this one, which is 931.49. In some books, they use 931.49, and this one is approximately 931.5. Okay, 931.5, and that's the more convenient number we are going to use in this chapter. Okay, please remember this number if you want to convert any mass in atomic mass unit to the energy. We have to use this one. Okay, 931.5. Okay, what else? We go ahead with this. The nuclear physics often express the mass in terms of the unit by using this one. Okay, from we refer to this number, mega electron volts per c square. Okay, that's another equivalent mass unit in from one atomic mass unit. It's correspond to 931.5 mega electron volt per c square. Okay. Yeah, this is the unit we are going to talk in the nuclear physics. This is the unit most people talk or consider in chemistry and so on, right? The next thing for us is the defect mass and binding energy. Now we get into the detail how the nucleus of any atom has been formed up, right? Has been arranged. Okay, the total mass of the it means we are going to see how the proton line and how the neutrons stay together in inside the nucleus. This is the nucleus, okay, a piece of nucleus which is in a spherical form, right? Where you could find the volume, the radius of that sphere. Okay, yes, the total mass of the nucleus is always less than the sum of the masses of its nucleons. The total mass of the nucleus is a single piece of the green one, mass of the green one of the nucleus, often less than the mass of the proton plus the mass of neutron. How many you have, right? It's Z and plus A by Z. I don't know where to write down. Okay, it should be less than oh, sorry. Yes, it should be less than A minus Z and mass of neutron. Okay, the particle the neutron particle, and that's the mass of nucleus. I'm sorry for that. The mass of the nucleus. Yes, the mass of the nucleus should be less than the mass of the summation of the mass by proton, which has to be multiplied by the number of protons you have in that atom, in the nucleus of that atom, and that's correspond to the set, right? The atomic number, and the number of protons, which is actually the number n here. Okay, this one is actually the capital N, right? Because N is equal to mass number, right? The mass number subtracted by the proton numbers, which is the atomic number. All right. This relation often hold from this sentence. The total energy of the bounded system in the nucleus is less than the combined energy of the separated nucleons. Okay, if you convert the energy from this mass and you convert the energy from this mass, and you want to find a difference, okay, you want to find a difference, so the energy from this side should be greater than the combined energy. All right, because the mass on the right hand side, the separated system, is greater than the mass of the nucleon itself. Okay, the difference in energy is called binding energy, which is the topic of this section. Okay, the binding energy of the nucleus. Okay, what is this? It is the energy that is transformed to be the attractive force or the nuclear force so that the subatomic particles can stay together without any problem. Okay, the binding energy can be seen as the energy that must be added to the nucleus to break it apart. Okay, you know the difference, and the right hand side here for the separated particles is greater than the energy caused by the single piece of the nucleus. And if you want to destroy or separate these nucleus into several neutrons and protons, into several nucleons, that's simply speaking, you have to add that energy, and that energy could be seen as the binding energy. Okay, if you put the binding energy into this nucleus, okay, they are going to be exploded. Okay, the neutron, the proton, and so on will be free from each other. It's like you destroy it. Okay, and the amount of the energy you can start to destroy is the amount of binding energy, and to separate them into neutrons and proton. Okay, and this energy is actually the amount of energy that try to keep all neutron and protons to stay together. Okay, that's the concept how the nucleus has been formed of, And for us in physics, right? For you in the high school level, we're gonna start to complete some calculate something regarding the nucleus of any atom. And the starting step is the starting step is the nucleus of the deuterium or the deuterium atom. Deuterium atom, the nucleus of the deuterium is known as deuteron. It's like nuclear is called nucleon, right? The nucleus of the deuteron is known as the deuteron. If you work in PhD topic and you are specialized in deuterium, the special word for the deuteron nucleus is deuteron. Okay, deuteron. Okay, what is that? We're gonna open another. This one, right? The deuteron, deuterium or deuterium, or where is that? Or maybe after that. Here, this the next page. Okay, deuterium is the next isotope. Okay, you can also say it's nuclei, right? Nuclei is a series of a nucleus. The deuterium is the isotope of hydrogen that has one neutron and one proton. Okay, and the atomic mass is not 2, but the mass number is exactly 2. Well, yes, we will call it. You know this one, right? It's called. This one has a single proton, single nucleon. It's called hydrogen, right? Hydrogen that has only proton around at the nucleus. Okay, in the nucleus, you have only a single proton. That's the simplest atom. And the next one is the electron, right? Electron is moving around. This is the atom of hydrogen. And the next one is H21, which is deuterium, right? It's deuterium. Okay, deuterium. I don't know why they say that. Sometimes they use even the letter D, okay, instead of hydrogen. Okay, but you know that deuterium is a family of hydrogen, right? It's an isotope of the hydrogen. It's hydrogen nuclei, right? It's a series of. It belongs to the family of hydrogen, deuterium. Sometimes, if you really work in the spatial field of the deuterium, they may even use D to be differentiated from hydrogen. But for us, we are not so specialized like that. So we will say hydrogen 2,1. And what about hydrogen 2,1? It means we have 2 nucleons inside the nucleus, and we have a single proton only because this is the atomic number. You cannot change it. Okay, it's proton and neutron. That's the deuterium nucleus. This is the deuterium nucleus, and you have a single electron moving around. Okay, you can say this is an isotope to deuterium. You can have even more one neutron. Okay, that can exist in nature. It's called tritium. Okay, tritium means the hydrogen that has 3 nucleons, right? You know, tritium or tri, which means 3, right? Yeah, and that's the case for us here. But for this example, they want to consider only the deuterium atom, okay, which is this one here. Okay, just the nucleus of the deuterium atom called the deuteron. consists of one proton, this one, okay, one proton and one neutron, okay, which is surrounded by the circle here. Calculate the deuteron's binding energy in electron volt. Yeah, calculate the binding energy. The way to calculate the binding energy is that you have to convert the defect mass or the excess mass. Okay, you can see them. You can say a defect mass. You have to convert first the defect mass. You can not first. Second step actually to binding energy. And before that, you have to convert the mass and so on, mass of the nucleons, right? Subatomic masses, right? To you have to process the masses to defect mass and convert the defect mass to binding energy. And the way to do this is use that relation, which is 931 mega electron volt per c square, which is one atomic mass unit, right? Okay, in order to do this, the excess mass or the defect mass is denoted by delta M. Okay, and yes, let's consider deuterium or hydrogen 2-1. If you are not familiar with the name, I'm also not familiar with hydrogen 2-1. Okay, it means that you have one proton, right? You have one proton. Oh, you have a single proton. You have one neutron. Okay, and the mass of the proton is known, right? You can take it from from this one, right? The mass of the neutron is right here. Okay, the mass of the neutron is right here. The mass of the proton is right there. And yes, in order to find, we're gonna find first the excess mass or the defect mass, right? The excess mass or the defect mass. The defect mass. All right, the first step is that you have to think of two masses. The first one is the separated mass. Okay, separated mass means you have to add the mass of proton plus mass of neutron, because you have only one piece of the each, right? So it's going to be where is that? It's the mass of the proton, right? It's this one, okay? Here in atomic mass unit, okay? It's the mass is 1.00002727, let's say U, okay, and plus the next one, which is the value of the mass of the neutron, which is 1.00866. 1.00866. That's the mass of neutron. Because because neutron has a little bit more mass than the proton, okay, and then you combine it, okay. And the next step is you compute the unified mass, which is already the deuteron, right? Deuteron mass. Deuteron, which is the nucleus of deuterium, deuteron mass. Okay, the heart or the nucleus of the deuteron, and the heart of the deuteron is provided here. Okay, okay, we neglect the mass of the electron. Okay, in this table, okay, you have deuteron, which has Z equal to 1, and neutron as 1, 2, and the mass is 2.01. Mass of deuteron, which is the H21, right, is equal to 2.01401, okay, unit, okay, atomic mass unit. And the next thing is the third step is that you have to compute the excess or the defect mass, right? The excess or the defect mass. How is that? It means you have to compute the delta M, which is the mass of proton plus mass of neutron minus mass of H21, which is the deuteron, right? And yes, once you put it into the calculator, right, you're gonna get somehow it's not much, okay, 0.098 and 94 atomic mass unit. Okay, it's not so high, but yeah, that's the whole thing. And yeah, that's the first step, right? The next step is that you have to convert. Okay, convert the excess mass to the binding energy, Okay, and the way to do that is the following. Okay, we open a new page. Okay, this is the excess mass, right? And the binding energy per the binding energy, it's E, right? E is going to be delta M times 931.5. Okay, after you use the Einstein equation, it's MeV per C square. Okay, and yes, this is that MeV per C square per atomic mass, and yes, you compute it. You put that number 0.09894. Okay, and here is 931.5, and you're gonna get somehow 92.16261 mega electron volt. Okay, and here is the binding energy, right? ไม่รู้ว่าคราวที่แล้วผมสอนถึง binding energy หรือเปล่า Okay, and yes, for us we have only no. Yes, oh no, I'm sorry for that. It's not 92. I'm stupid. It's not so high like that. It's only 0029. Stupid. 002388, right? And you convert it to mega electron volt, is going to be 2.224, right? It's the energy, the binding energy inside the deuteron, right? The nucleus of the deuterium or the hydrogen 21. the isotope of the hydrogen that has one neutron, okay, is on the orders of mega electron volt is 1 million higher than the energy on the electron scale or electron orbit scale, right? And that one is on several mega electron volt. This one is on mega electron volt. Okay. The next one is the problem. Find the mass defect. Okay, let's go further and realize that this example, right? Now, right here we write down the mass defect delta M equals mass defect of what? Find the mass defect of the total binding energy and the binding energy per nucleon for the common isotope of carbon carbon 12-6. Okay, you know that carbon has 6 protons, right? And there are also 6 neutrons inside these. Okay, let's draw what's going on with carbon 12. Carbon 12 has 6 protons, and it also has 6 neutrons. 6 neutrons. Okay. How is that? You just draw 6 protons, 6 circle of proton, which is quite a lot actually. Okay, you have 6 protons, but you need to have also 6 neutrons. Already 6. Okay, and here this is the nucleus of the carbon. Okay, and you're gonna have electron of 6 electrons too, right? Moving around this nucleus. Okay, you have 6 orbits of electron. 6 orbits. Yes, and we are not paying attention to the electron orbits because we are talking about the nucleus of this carbon 12. Okay, the mass defect is the first thing you're gonna need to find, right? Mass, the defect mass, I'm sorry for that. Defect mass. The defect mass, right? Defect mass in this sense is gonna be delta M, right? Delta M, of course, you have 6 protons, you're gonna have 6 mass of 6 masses of proton, this one, and 6 masses of neutron too, right? No, and you have to reduce or subtract it by the total mass, the mass of the carbon 12-6. Okay, and let's get into the detail. The delta M is 6 times the mass of the proton, and of course mass of the proton is known here, 1.006,825 atomic mass unit, of course, and plus 6 of mass of carbon 12, 6 of mass of neutron, 6 masses of neutrons, 6 masses of 6 pieces of neutron. It means 1.000866649 atomic mass unit 2. Okay, and then you need to subtract it by the mass of the carbon 12. Let's go to the table and see how the carbon 12 is. Carbon 12 is this one. Okay, carbon 12 is exactly 12. Okay, exactly 12 atomic mass unit. Okay, because this is the reference element to the other. Okay, and yes, you could get the result after subtraction, right? It's 0.09894 atomic mass unit. And the next thing is you have to consider binding energy. Binding energy. How is that? You just say energy is equal to delta M times 931.5 MeV, mega electron volt per C square N. And of course we got 0.09894 atomic mass unit, right? And 931.5 mega electron volt per C square. Okay, and yeah, you would get the result approximately 92.162.61. 6261, and the unit is mega electron volt right now. Okay, and yeah, that's the binding energy. But they also ask us about the binding energy per nucleon. Okay, the average binding energy. Energy per nucleon. Okay, how is that? You just divide this. Okay, you just divide E by the number of nucleon, and the number of nucleon is denoted by the letter A, right? Which is 92.16261 divided by the mass, the number of nucleons, which is 12, right? Because if we have 6 proton, we have 6 neutron. And after the calculation, you get somehow 7.68 approximately. Okay, MeV per nucleon, and that's the answer to this problem, right? This one and this one. Oh no, binding energy is not. The experiment is not. They also want to find excess mass, right? The mass defect is also all right. Okay. Yeah, that's the results from defect mass and binding energy. And let's see what happened. The binding energy per nucleon is 7.68, right? For the deuteron, right? The first hydrogen that start to have neutron. Okay, if we consider the plane or the typical nucleus of the hydrogen, we don't have a defect mass. So we won't have defect mass at all, because we have a single piece of proton, right? So there is no other subatomic particle inside the nucleus. So there will be no interaction between two particles, because we have only a single particle. Yes, the energy per nucleon is denoted by, is on the scale of 7.6 for the carbon 12 and 2.24. Okay, 1.1. Okay, if you divide this one, the one here for deuteron, right? For deuteron, if you divide by A, and A is number 2, right? It's 2.224 divided by 2. It's going to be 1.112 MeV per nucleon. Okay, so what is that? 1.112 and 7.68. 1.112. 1.112 is here, the location of deuteron. Okay, deuteron is somewhere here. They start to have here, and carbon is somewhere here, right? It's 7.8 blah blah blah, 7.6 blah blah blah, right? And yeah, the nucleus that has more binding energy per nucleon would have more strength. Okay, that atom is stronger than other atoms that have lower binding energy per nucleon. Okay, and that's the typical way for the physicists to investigate the strength of several objects, of several atoms. Okay, and they have done, okay, many physicists have computed the binding energy per nucleons for several particles, for several atoms, and it turns out that ferrite, which is iron, and nickel, right? Nickel is the next one. The strip here, the brown one or the yellow one here, has located in the highest area that has the maximum value for the binding energy per nucleon. It includes ferrites, iron, right, nickel, and germanium, right? And the value for the binding energy is around almost 9 mega electron volt per nucleon. Okay, and after that you go for silver and gold. Okay, it's less than that. It's okay. This is the number of nucleon. Okay, you have more nucleon is no longer stable. Okay, because the binding energy is smaller. Okay, we cannot change any curve. Okay, this is the nature that we get. Okay, that's the plot from book number 1. For the book number 2, they also provide a plot of the binding energy per nucleon. We have 1, 1, 2, right? For the deuteron, we have the 7.68 for the carbon 12, and the highest amount is around nickel, right? Almost 9 mega electron volt per nucleon. And one important thing in this figure is that you could see here that the helium-42 nucleus, which is denoted by here, He42, has a typical something different. Okay, has something different from the neighbors. It has higher, extremely high binding energy per nucleon compared to this area. But this is the small nucleus. This is the small nucleus. So once you have something high like this, that's already good. The next one is the radioactivity. In 1896, Becquerel, right? Becquerel is, I think he's from France, start to observe the uranium salt crystal. I don't know it's happy, but in that time, at that time, the science might be quite popular. And yeah, the physicist or the chemist, I think Becquerel is chemist, accidentally discovered the uranium salt crystal that emits an invisible radiation and that can darken the photographic plate. Okay, it means there should be some emission of particle from that object, right? Okay, even if the plate is covered to exclude light. Okay, yeah. We cover the plate by something, okay, so that there will be no light to hit that photographic plate, but becquerel still can observe something on the photographic plate even we protect the light. Okay, this spontaneous emission of radiation was soon called radioactivity, okay, because there is a small particle, tiny particle emitted from the radioactive object. And Marie Curie and Pierre Curie reported discovery of 2 previous unknown elements, both of which were radioactive, known as polonium and radium. Okay, yeah, they are coupled to each other. In yeah, they also discovered polonium and radium. Where is that? Polonium, right? Polonium. Oh no. Table of element. Okay. Okay. Where is that? Oh no, this is German. Table of elements. Okay, this one for you in English. Okay. Polonium. Where is that? Polonium is here. Okay, it's it's a big atom, right? The element after bismuth. Okay, bismuth is 83. Carbon is 6, right? Polonium is 84, and radium, right? Radium is here. The couple there. Marie Curie and Pierre Curie have also discovered radium, which has the number of protons as 88. Okay, there are 88 protons inside radium. Yeah. What else? Subsequent experiment by scientists show that other substances were also radioactive. Okay, not only polonium and radium. I don't know. Maybe you have some chance to keep out of this big object. Not big. The object that has bigger nucleus like this. Okay, around greater than 84. Okay, and yeah, this far also there are some radiation from those objects. Radioactivity was the result of the decay or the disintegration of unstable nuclei. Okay, because when your nucleus is too big, okay, they are not stable, and you know already, right? Why the nucleus is not stable? Because there will be repelling force, okay, caused by protons and so on, right? And the way to hold that big nuclei is that you need to add neutron, okay, to join the existing particles to stay together, because adding the neutron is equivalent to adding the attractive force to the nuclei. Oh, yes. Yeah. But once the nuclei is very big, okay, they are gonna disintegrate automatically itself, or they're gonna reduce its size to be smaller one. There are 3 types of radiation that can be emitted by radioactive elements, and we will consider later in this chapter. I don't know what time for us. It's 14, right? 14. We still have 22 minutes. Okay, there are three types of radiation. The first one is alpha particle. The next one is beta particles, and the third one is gamma ray. Okay, gamma ray is not actually the particle. It's actually not any particle. It's only a kind of high energy photon. But these two are really subatomic particles. This one is equivalent to the nucleus of the helium-42. Okay, you know, helium could be helium-32, helium-42, right? That's the possible isotope for the helium, right? Helium-32 is this helium. Helium-42 is the typical helium, which is called helium-42 with our energy is called alpha particle. Okay, the ionized version of the helium-42 is known as alpha particle. And in chemistry, they use helium-42 with 2 plus on the right hand side, on the right superscript. Okay, the first particle is the big, which is the big object, big particle. It's the nucleus of helium-42. The second particle is small, and this is quite well known to you. One of these is one of both is electron, right? The electron is much smaller than even proton, right? But alpha particle has 2 proton, 2 neutron, right? Electron is even less than a single proton, a single neutron, right? So it's much smaller than the electron is much smaller than the helium-42 particle in this way. And I don't know why they say it's beta particle, but actually it's the emission of electron. Electron is moving out of that radioactive element, and even more than that, beta emission could be beta minus decay, beta minus process, which means they emit the electron. And later on, the physicists have discovered that there are also another type of beta emission, which is called beta plus emission, and it emits a new, I don't know, maybe it's not new to you because you have already seen the standard table of the subatomic particle, right? The positron, right, which has exactly the same mass as the electron, but it has the opposite charge to electron, and this one is quite difficult to detect, but it's not beyond the ability by human. Okay, the positron and the electron could penetrate a few millimeters of aluminum, right? If you want to protect this beta particle and alpha particle, you need to use metal like aluminum, right? Yeah, you may have ever heard that once the nuclear power plant explodes, there will be emission of several radioactive particles, right? And two of that have been already addressed here: the alpha particle, beta particle. The ability of the because this one is big, right? Alpha particle is big. It has 2 protons. It has 2 neutrons. The nucleus is big. They cannot penetrate because they don't have enough kinetic energy. They don't have enough energy, so their movement is not so strong, and they cannot penetrate the sheet of paper. But for the beta particle, it's a tiny particle, right? Electron is much smaller. Is, I don't know, 40,000. Okay, in size less than in mass less than the neutron or proton. So because it is small and it has high energy, they can penetrate a few millimeters of aluminum. Okay, it's quite dangerous too, right? Gamma rays, gamma ray is a kind of ray emitted by high energy photon, and it can penetrate several centimeters of lead. Okay, here is millimeter, but this one is very small, small mass, right? But gamma is a high energy photon. It has a high penetration ability. Okay, they have a high penetration ability. It can penetrate several centimeters of lead. Okay, yes, the way to classify which layers, for example, you have a single source that can you have a single source of radioactive object, and with this object, the electron could go out. Okay, the helium-42 nucleus could go out, and it can also emit the high energy photon, which is known here as the gamma ray. Okay, three particles, three emissions could take place from this source. Okay, and the lead, which is thick enough, okay, they use lead instead of aluminum, because lead may have more stopping ability to the penetration. They have high prevention ability. So the mixture of source that emits alpha, beta, and gamma rays, and once it go along this hole or this strip, okay, and what else? And if we leave the magnetic field like this, okay, because the physicist is often a clever person, okay, they could design the measurement in a clever way. And once you leave the magnetic field, and you know that the X symbol, okay, the X symbol represents the tail of the arrow. It means the magnetic field light is pointing toward the plane of this light. Okay, this is the tail of the electromagnetic field lines, and what you could see is only the tail, the rear part of the magnetic field lines. And from what you have heard before, right, F is QVB, and you have to use your right hand to cross, and in order to find the cross and then find the induced force, right, F is QVB. I hope that you could still can remember from the previous QV cross P, right? Velocity vector is here V, beta, B vector inside, right? And you cross, you start from V to B, you're gonna get the induced force in this direction. Okay, and it will bring the subject somehow always perpendicular to the tangent path, right? So this one start to rotate in like in a circle manner. Okay, if you let it go in this area of the electromagnetic field, you're gonna get a circle movement. Okay, that's this formula is valid for the positive charge, right? But if this one is if the charge is negative, F is going to be reversed. For example, if you have beta minus decay and it always emits electron is going to be out of this one. And yes, because Q is negative, it's negative 1.6, that's the value for the electron charge, right? And there will be force all the time here. There will be the same color. You will have all the time force in this direction, and here you would have force in this way. Okay, yes, because of the QVB expression, but you need to use the reverse version because Q is negative, so you get the force in the opposite way to the red one. Okay, from the helium-4 to the alpha particle. And yeah, that's all that will bring us to the circle movement right here. And if we don't have any charge at all, like a photon, the high energy photon, once it moves from the hole here, it has no effect, no magnetic induction or force induction to their movement here, right? And yeah, there will be no deviation from the straight line at all, because its charge is neutral. Okay, it's neither positive nor negative, so you get the straight line movement for the high energy photon gamma. All right. Yes. The next thing is we're gonna see. Okay. Yeah. These are three layers that we could observe from the radioactive element. One of the 2,500 unknown nuclei, only 300 are stable. Okay, this is the species of nucleus or species of nuclei. Only 300 family are stable on Earth, right? We don't know whether somewhere else outside the Earth you may have more nuclei, but the experiments for human era right here is 2,500 samples, right? Around that, and only 300 are stable. The remaining ones decay. Okay, the 2,200 nuclei will be subject to emitting particles, transforming themselves into other nuclei. Okay, they can emit the particles like helium-42, and they can split themselves to a smaller nucleus or nucleus. Okay, nucleus is unstable if it's too big, if that is greater than 3, which is bismuth, and if the number of nucleon is greater than 209. Oh my God, it's very big, very big, very big. I don't know, very big nucleus. Okay, and that's the first two conditions. Or if the neutron proton ratio is wrong, and here comes the beta decay. Okay, because when the ratio between proton and neutron is not good, okay, they are going to emit electron, and that's beta. They want to form of the proton. Actually, they want to transform the neutron to proton or transform the proton to neutron, and the product after this transformation is the electron. Okay, and yes, similar to atoms and molecules, nuclei have internal motion. Okay, and internal motion causes the high energy, right? Internal motion means that there is vibration, and when the nucleus has vibration, it means it's not in a stable state, right? Because they process the energy, they have the energy at that time, at that moment. That's why they have internal motion or vibration. And with this vibration, if they want to reduce their energy state to the stable one, to the ground state, they need to emit the energy, and the energy that emits will be in terms of ray or the lights. And yes, and that's called gamma ray. Okay, and yeah, gamma ray is the result for the nucleus that tries to be kept stable. Okay, and that tries to keep itself stable. They have also set up allow energy levels, including ground state and exciting state. It's like energy orbits of electron. Okay, due to the great strength of nuclear interaction, excitation of the nuclei are typically on the order of 1 mega electron volt. If you compare it to the electron scale, the electron order, they have the energy on the order of few eV, right? But this one, it's written as 1 mega electron volt. Okay, on this scale, the nucleus always remains in its ground state. Place it in an excited state. Nucleus always remains in its ground state. Place it in excited, nucleus can decay to the ground state by the emission of one or more photon. Sometimes it's known gamma rays or gamma rays photon. Okay. With energy on the order of mega electron volt, you could see that the gamma ray is very, very strong, right? It's dangerous if you let your body to touch or absorb the gamma ray, like the people who are working in the nuclear power plant. Once the power plant is exploded, you have very, very high chance to get gamma rays, and then this can cause cancer to your body. Okay, because this one has high energy. It's like you put your hand into electromagnetic wave, okay, and your hand will receive the energy from the electromagnetic wave, right? We still have 6 minutes left. Right? The disintegration of the nuclei that do not meet the stability requirement is called radioactivity. Okay, once they are not stable, the nucleus is known as radioactivity. Okay, the next thing is the decay rate. Observation has shown that if a radioactive sample contains a radioactive nuclei at some instant, so this is the starting amount of radioactive nuclei, and the number of delta N, the number of nuclei of delta N that decay in small interval delta T is proportional to the initial amount N. Okay, what does that mean? If you want to observe the transform of nucleus, okay, the amount of big nuclei that has been transformed to the smaller one divided by time will depend on the number of the nuclei at the initial state, which is N here, and the dependence here, the proportionality here could be written expressed as the equality, but it's not the increasing relation, right? It's a decreasing relation. That's why we have negative here. With the assumption that we assume that the lambda, which is known as decay constant, should be always positive. Okay, if this one is negative, we don't need to have negative sign here at all. But let's say the decay constant is only a simple value, it's a positive value, and the rate of change of the number of transform or disappear nuclei per time, or the rate of change, will be equal to negative, and this is the constant, right? And negative means reduction times the number of the initial nuclei at the beginning. Okay, the decay rates is known also as activity. I don't understand why this. Okay, the decay rate is the absolute value of this rate of change, because rate of change is negative. Decay rate is only a positive version of the rate of change, and after the absolute value, you just throw away the negative side, right? You get lambda n, and I is equal to lambda n is known as the activity or the decay rate. You need to remember this value, which can be either in Curie. Okay, the rate of change. Of course, we don't talk about the negative part and the negative idea, right? Everybody know that the big nuclei will be split into smaller nuclei once the time goes by, right? Okay, the unit of rate of change could be simply Curie, right? Curie is the famous. Okay, is the Curie, whether Pierre Curie or Marie Curie. Both are the pioneer of radioactivity. Okay, in one research group, and the one. So the physicist has formed up the unit in with under the honor to them, to both of this pair, this husband and wife, as Curie. One Curie is equal to 3.7 times 10 to 10. Okay, what is that? 3,700 million decays. Okay, the number of reduced nuclei per time per second. That's the 3,700 million nuclei reduced per time is known as 1 Curie. And Becquerel is the original person, the first person who stated something about activity. And Becquerel is denoted as the single SI system for the decay rate or the activity here. 1 becquerel is equal to 1 decay per second. You know, becquerel is not appropriate, right? Because a single piece of something contains trillion and trillion nuclei, right? So becquerel is only ideal unit, okay, because we want to give the honor to him. He was the first pioneer in radioactivity, but 1 decay per second, 1 nuclei per second, that is not meaningful. Okay, the Curie unit is more appropriate to that. Okay, next time we are gonna use the calculus to talk something about half-life. Okay, half-life, and how to determine the remaining amount of nuclei after the transformation to the smaller one, because they are not stable. Okay, we will talk about the elements that are radioactive. Okay, they try to change their big size of nuclei to the smaller one. Okay, so it's time to finish so that you could take a break, right, for next subject in this afternoon. Okay, thank you very much. See you on Friday. All right, and if you have any questions, just let me know. If you didn't write down your name in any matter in Zoom, in YouTube, just write down. Okay, then see you on Friday. สวัสดีครับ บ๊ายบายครับ 604. And in Zoom too. CD, 151. Go classroom. Just smoking from smoke. Oh. But this one is incorrect. Okay. Okay, Supravit M605 has arrived. Okay. Okay, now anyone want to join in Zoom มีไหมครับใครจะเข้าที่ Zoom ครับanyone who would like to join in Zoom yes okay no one right no one want to join in Zoom right okay yes let's get back to the what's this one right see reversing all these things. Yes no one want to join Zoom right yes the next one is M605 right so the section for M605 we're gonna open the 605 today file and ไม่ต้องใส่หูฟังนะครับ test sound again yes Thanakon M605 has arrived test 1 2 3 okay fine yes the next one is the next one is M605 at page 41 okay page 41 right we go to 41 for M605 41 right here yes M604 was just alive at the decay rate and you have already passed passed the decay rate right the story about decay rate and it's time for you to tackle the alpha decay which is the first type of decay in the next one will be beta decay and so on right? Beta decay gamma decay and after that we are going to talk about the carbon dating right gamma decay is not so so meaningful right? it has nothing so complicated okay there is nothing complicated for the gamma decay in what else the first one the first two decays alpha decay and beta decay are quite complicated okay there are many things to do with that gone just alive and yeah you know there are 3 channels waiting for you anyone want to join Zoom no huh? So yes we go to the alpha decay right we go to alpha decay let's start with that in alpha particle can be expressed as alpha 42 okay alpha 42 like this alpha particle, right, is denoted by the alpha alphabet here. And this is actually the nucleus of helium-42 with the superscript 2+. 2+ mean we throw away the 2 electrons around the orbits, around the circle of the nucleus. You have here proton, you have here neutron, you have here neutron, and here you have proton. This is the helium-42 nucleus. Okay, helium-42 and 2+, because this is the ionized version. Okay, there are no 2 electrons, so without 2 electrons, it's only the nucleus, and that's why we call helium-42 it 2+. Okay, ionized version of the nucleus, ionized version of the typical helium. Actually, helium should be bigger because it should have 2 electrons moving, right? Okay, but at this state, okay, we consider only the heart or the center of the nucleus, okay, which is only helium-42, okay, without electron at all. Okay, helium-42 denotes the helium ion with 2+ E sharp. The mass of the alpha particle is around 4 atomic mass unit per atom. The mass of this piece only, right? Only the nucleus is around 4 atomic mass unit. In it's not exactly 4 atomic mass unit, but rather approximation. And if you go into the detail, it's 4.00 blah blah blah. Okay, there are some minor digits after the decimal point. The mass of helium-42 or alpha particle 42 here could be expressed as 66 or 446 blah 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 with the uncertainty 82 for the last 2 digits here, and times 10 to negative 27. Okay, it's in the same scale as the the proton and neutron, right? But the one proton is around 1.67 times 10 to negative 27, but this one is 6.6. You could see that it's around 4 times the mass of the proton or the neutron, right? So that's why we end up with 6.6 10 to negative 27 kilogram. Alpha decay is the decay of a nucleus that emits an alpha particle. And the process of these emission could be written like this. Okay, you start with this one, right? You start with the initial atom, initial element, which is the big one, right? Let's say it's atom Y. Okay, it's element Y. It has mass number as A, which is the number of nucleons inside the nucleus, right? The number of protons and number of neutrons together, right? And here is the number of protons in yes, it's because this nucleus is not stable, right? It's too big. The number of the ratio of proton and neutron is not appropriate, and somehow, right? When the nucleus side is, when the atom is bigger than bismuth, so that atom is no longer stable, and it's going to be split automatically to the lower one. Okay, and one of that way is to be split into a smaller atom and a smaller nucleus and helium-42 atom, which is the alpha particle here. Okay, and you get the alpha particle, which is a tiny object compared to the X1, right? And yes, This one is going to move if there is some remaining energy after this disintegration, after the separation. If there is energy, both objects, both particles will move. Okay, but the smaller one, like alpha particle, would receive more energy. They're gonna spin very fast, and they're gonna move very fast, and that's might be dangerous to us. Okay. How could we observe? Okay, let's take a look at the upper row here. Okay, you start with A, and here is deduced or subtracted by 4, right? Because you have to separate 4 nucleons for the nucleons inside the helium-42 or the alpha particle. You have to dedicate 2 protons to build up a new nucleus, which is called alpha particle, right? 2 protons for that. So you start from Z, right? This one would be Z minus 2 because 2 of protons have been reduced to form up a new particle, and 4 nucleons have been formed up to build a new particle, which is the alpha particle here. Okay, and from Y in the big nucleus you get a smaller one, but I'm not sure this one is already stable. Okay, if you start from a very big element, this might not be stable yet. Okay, it's gonna need to be split later. Maybe it can happen. Okay, Y is called in the vocabulary of nuclear reaction, it's called parent nucleus. Okay, the starting element is called parent nucleus. We consider only the nucleus. Okay, we don't talk about the full atom with a complete electron and so on, right? X is the daughter nucleus. Okay, the smaller atom that has smaller nucleus. Okay, and yeah. And here is the alpha particle, which is the title of this topic, right? Alpha decay. Yeah, this is the general process for the alpha particle, for the alpha decay. In yes, of course, you could the equation 38 could take place to any element, and one of the most happened situation is something about uranium and radium. Okay, uranium has the atomic number as 92, and radium has the atomic number as 88. You may have ever heard the word uranium quite often, right? Because it's the name of the radioactive element, which is quite popular in daily life, in the human life. Okay, let's take a look at the location of uranium and radium, 88 and 92. 88 and 92 is the place where you could find here. 88 is radium here, and 92 is somewhere here, uranium. Okay, it's alkali actinides. Okay, it's the radium alkali earth, alkali 2, right? Yeah, uranium actinide. This is radium alkali earth. Okay, 88 and 92 are the main 2 elements. We could find the alpha decay. We could get the helium-42, which is the alpha particle from these 2 elements. All right. Yeah. Let's get back to our lecture notes. The next one is we will consider equation 38 for the case of uranium. We will consider 38 for the case of radium, which is the 88 and 92. And of course, for uranium, you have 238 as the number A here, right? The value for A. 238 minus 4 is going to be 234, and that's why you have 234. And you get, of course, the helium-42, which is the alpha particle, right? In you start from uranium 92. In the outcome here should be have 2 missing proton, right? The number of protons should be reduced by 2. So it's going to be Z minus 2. You start from 92. 92 subtracted by 2 is going to be 90, and 90 is here. And how come TH? Let's get back to the periodic table. Go start from uranium. You get you end up with 90, which is this one. Okay, this element is called thorium. Okay, thorium actinide. Thorium actinide is denoted by TH, so we will see TH as the element here because now the atomic number has changed from 92 to 90. You get TH as the new element. Okay, and as you know, whatever symbol here need to correspond to the atomic number, which is the number of protons, because now the number of proton has decreased, okay, by 2 from 92 to 90. So the element changes also 2. Okay, go to the left side by 2 step 1 and 2, you reach thorium. So the outcome will be thorium, and that's why you get here thorium 234. Let's talk about the number of nucleon. Nucleon, okay, nucleon is not addressed here about for thorium. It's no problem. Anyway, we get 2 object rates, thorium and helium-42, or N for particle, which is N for decay here. It means the decay of uranium, the big element, and the outcome is together with the helium-42, the alpha element. Okay, and radium 88 is the starting point, right? The big alkaline rare earth element. And we will apply 38 to radium. You have 226, which is the number of nucleon, which is the mass number, right? The mass number 226. You need to be subtracted by 4. Okay, you have to reduce the 226 by 4. So 226 minus 4 will be 222. Okay, 3 times of 222 here. That's the remaining nucleon inside the nucleus. Okay, nucleus of this element, I don't know. And just that is the atomic number, the number of protons. You start from 88, right? 88 from the big nucleus. You have to be reduced by 2. Okay, the reduction of number of protons by 2. So 88 minus 2 will be 86, and that's why you get 86 here. Okay, and once the number of protons or the atomic number changes, you start from radium, you need to go back by to 86. Where is that? 86 is here. 86 is here. It's called radon. Okay, radon is a kind of noble gas. Okay, the gas that has layer interaction to the other. Okay, because noble gas is a kind of stable gas, right? Because the nucleus is quite stable. They're gonna have any chemical interaction to any other element, so it's already stable. So that's great. I'm not sure about thorium, but uranium will end up with thorium. But from radium, they stop at radon, which is a kind of noble gas and has layer interaction to any other element. So that's good for radon. Okay, radon is denoted by 86, right? 86 is denoted by R and N. Okay, when now the number of protons or the atomic number changes, we have to use a new element symbol. Okay, not Ra anymore. We have to change it to be Rn, and that's the reason why we get here Rn. And of course, according to 38, we should have the smaller particle 2, which is called helium-42 or alpha particle. And that's the most notable two processes in the alpha decay. You start from uranium and radon, you end up with thorium and helium-42 or alpha particle. You start from radon, radium, you end up with radon, which is a noble gas, and you have also the alpha particle after this integration. Okay, let's talk about the realistic result after this decay, after this process. Okay, because this is the one directional process, from the big one to this one. Okay, I have never heard that these two things will be combined to the left hand side, but this is only a single direction that could take place. Okay, the half-life of uranium to be split into thorium and alpha particle is 4.47 times 10 to 9 years. Okay, your uranium will be split automatically somehow. This how many? 1,000 million years. My God, yeah, 4,470 million years, right? So it's quite long. That's the half-life. Okay, and then the uranium will not completely disappear. Okay, they will just remain as half of the initial amount. And in the same way for radium 226 and 88, the half-life is 1.6, 1,600 years. Okay, the radium will remain half of the initial amount. Okay, and that's the thing that could happen. You could see 1,000 is very, very long, right? It's quite a long time. Yeah. Let's go further if you want to see how the real picture takes place, right? For the radium process, it's 226 and 88, right? 226 and 88, you have 222, right? 222 and 86, which is the radon and the noble gas. You have helium-42 or alpha particle. It means there are two protons, two neutrons, okay, inside this red circle in this sphere, the red sphere. And you could see that they also draw the arrow here, the green arrow, which means they move. Okay, they move in the opposite way. And as you observe, the length of the arrow here is short. The length of the arrow here is long, right? It means that the smaller nucleus, helium-42 or alpha particle, has more speed. Okay, has more speed or velocity than this one. But from the vector point of view, they are negative version to each other because the direction of the movement is opposite to each other. The nuclei 226 radium 88 decays to the radon 222 86, right, to radon and alpha particle, right? It's taken from book number 2. Okay, yes, in figure 8, the speed of the alpha particle. Okay, now you could observe the it's like the chemistry reaction equation, right? But it's the nucleus splitting equation, and here is the figure. But in physics, they will not just stay like two particles like these, because there is a plus sign here with additional energy, and this energy will be dedicated to these two objects, these two particles, right? So for this case, the energy will remain to both helium alpha particle and radon particle. The speed of the alpha particle can be determined from the curvature. Of course, because this is the tiny particle, it's very hard to observe the speed or the velocity of this one, right? To determine the speed or the velocity of these two tiny particles, it's very hard. We're going to use the magnetic field so that we could determine radius of the movement from this expression, okay, the charge of that object and the magnetic field strength, right, charge of that object and the mass of that object, the velocity of that object, right? If you want to find v, you just find the radius after this one has start to turn around or complete a circle. Okay, once you could measure the radius, you could bring it back to the velocity of this object, right? Which is RQB divided by M. Okay, the way in physics is something like that, because you cannot measure directly the speed of the alpha particle or the speed of the radon nucleus. Okay, the physicist uses this technique, the radius. After you put the magnetic field, okay, you put the magnetic field, this one will not go in a straight line. Okay, they will not go straight, they will turn around like a circle, as you have seen in the last chapter, right? In the previous chapter, in the last semester, there will be force, right, acting on the particle, and yeah, we will be RQB divided by M. The way that the physicists try to observe the speed of these two objects. Okay, the physicists determine the curve, the speed from the curvature of its trajectory by using electromagnetic field. It turns out to be, okay, the speed that they could observe. Okay, once they calculate from this expression, the speed of the alpha particle is around 1.5 times 10 to 7. It's around 15 million meter per second, right? It's quite high, right? It's high enough, but it's not. It's 15, right? It's quite close to the speed of the light, but 3 times 10 to 8, right? Yeah, it's 15 times 10 to 7. The kinetic energy of the alpha particle with this speed, okay, could be also observed. Okay, could be calculated, and you know that K is 1/2 mv squared, right? But this is the subscript for the alpha particle, which is alpha 42, and here is the mass of alpha 42, and v is the speed by using this value, right? The speed from this value, 1.5 10 to 7 of 15 million meter per second. 1/2 6.64 10 to -27, right? That's the mass of the helium-42, or the alpha particle. You start from here, right? The exact value for the mass of the alpha particle is somehow this is 6.644, and that's the approximation without the last three, the remaining digits after the 3 position from the decimal point. Yeah, the same thing is times 10 to -27 kilogram in the SI system, and this is the measurable value of the speed that the physicist has investigated. So we substitute 1.5 times 10 to 7 meter per second into this into the conventional expression of the kinetic energy, right? 1/2 mv squared. And after that, you put it into the calculator. You're gonna get 7.47 times 10 to -30 joule. Okay, and this is the energy, the kinetic energy in the SI system, right? SI scale. But yeah, you could see that this amount is not convenient, is very tiny, is 10 to negative 13, right? 10 to negative 13 is very, very difficult to observe, right? And yeah, it's better because we are talking about a subatomic particle, the nucleus, right? Something very tiny. It's better to change the scale, okay? And one of the most reasonable ways is that we turn into the same way as the previous chapter, right? Where the energy is observed in the electron world, right? Because they are considering electron movement and so on. So they just divide by the electron sharp value, 1.6 times 10 to negative 19. You get somehow electron volt, it's I don't know, it's million, right? 10 times 10 to 6, 4.6624073 mega electron volt, and that's the kinetic energy. That's the kinetic energy for the alpha particle with the speed. Okay, you could see that the energy of the alpha particle is around million order, right? Million times higher than the energy of electron movement in the atomic orbit, right? Okay, that's the amount of the kinetic energy we could observe from theory, from the result that the physicist has measured the speed. The next one is we will consider also the momentum, because yes, of course we have a static piece of radium, right? The big nucleus at the beginning, before decay, it just stay constant like this, okay, without any movement. So when there is no movement, we're going to have kinetic energy of radon as 0, because of course there is the m, right, the mass, but v square, once v is 0, v square will be 0, and 1/2 mv square will remain also 0, right? And the momentum for this will remain also as 0, because v is 0, right? When the speed is 0, no matter how you get the mass, okay, no matter how much you have the mass, the momentum will turn to be 0, because there is no speed. Okay, at the first state before decay, there is no kinetic energy, there is no momentum, right? Everything stays. The sum the momentum in total is 0. That's before decay. And after that, after the decay, the radon move to the left hand side, the alpha particle move to the right hand side, and yeah, there will be kinetic energy from the radon, and there will be kinetic energy on the alpha particle. And because momentum is a vector function, right? It's the velocity scaled by the mass of that object, right? P is equal to mv. You could, I hope that you could still remember this formula, right? P is equal to mv, and yes, P is equal to mv will be the P is equal to mv is the conventional expression for the momentum, right? But at the beginning, there is no momentum, right? This is also a vector of 0. Okay. The summation of the momentum from both particles should remain the same as the beginning, and that's the rule of momentum conservation, right? The momentum conservation principle. And the energy, kinetic energy, should also remain the same. Okay. Yes, as 0. oh no, it's not the case. The momentum should remain the same, but the kinetic energy may not remain the same. Okay, because it's a scalar value, right? After the decay, the nuclei of radon 226 radium, sorry, the nuclei 226 radium, the radon 222, 86 radon and alpha particle have their own kinetic energy and momenta. Okay, they start to have their movement, and that's why they have momentum and kinetic energy. They have kinetic energy and momentum. Okay, now let's talk about the numerical problem to alpha decay. Let's draw something here. Okay, given the atomic mass of radon 88, of radium 88 to be, of course, you know, this is the mass number. Okay, let me write down for the radon, for the radium. I often pronounce radon. It's not radon, it's radium. So mother, oh no, parent, I'm not sure. What is the word? Parent nucleus, okay. Okay, parent nucleus, parent nucleus, right? Parent nucleus will be parent nucleus will be radon, right? I'm sorry, radium 226 and 88, right? So the mass number, right? First, the mass number is 226, and atomic mass for the radium, atomic mass is not 226. Okay, atomic mass is this one, is 226 025,402 atomic mass unit with the unit U. Okay, it's the real mass compared to the carbon 12. Okay, this is the value compared to the carbon 12. This is the number of nucleon, right? Number of protons and neutrons inside the nucleus. It's exactly integer value, right? Because you cannot count the number of proton and neutron as the fractional number. Okay, it's only the integer. Atomic mass could be a fractional value, okay, because it's the ratio with respect to the mass of the carbon, right? 1/12 the carbon 12 mass, right? It could be a fractional number, so it doesn't need to be an integer at all. That's something about radium, but for radon we have 222 and 86. Okay, in this one we have mass number as for radon is 222, and the atomic mass for radon is not 222. Okay, it's not exactly to that. It's the value that this problem has provided. It's 222.017 and 571 atomic mass unit U. All right, and that's the whole thing in this radon. And of course, the information of the helium-42 or the alpha particle. This is only the nucleus, right? The mass unit, sorry, the mass number, of course, it should be 4 because there are 2 protons, 2 neutrons. Mass number is 4, right? You could count it as integer, right? And the next one is the atomic mass, right? With the real mass, atomic mass, right? This is the version together with the electron mass too, right? But we forget the effect of the electron at the moment, helium-42. Atomic mass for the helium-42 is 4.002602, and the unit is atomic mass unit, right? Like this. Okay. Yeah, that's the information. That's the information the problem has provided. The question is that calculate the amount of energy liberated in this decay. Okay, what is the energy released from this process? Okay, and that's the task we have to find. Yes, of course, you could take a look at this, right? You start from this process, right? You start from this big radium, and you get a smaller one like this, and you get a smaller, a much smaller one, which is helium-42 or alpha particle. 40, right? We need to end up at 1540, right? Okay. Yes, the mass of this one, right? It's gonna be okay. The first thing we need to find is energy liberated in this decay. Okay. It means the energy, right? Liberated energy. So this one is the quantity we want to find. But first of all, we have to compute the excess mass or the defect mass, right? And it's going to be converted to energy, the liberated energy, by using 53931, right? 931.5 mega electron volt per atomic mass unit, right? And that's the mega electron volt per atomic mass unit. I'm sorry for that. The unit here should be also. Oh no, not this one. Is for M604, right? Okay, we're gonna use 931.5 mega electron volt per atomic mass unit, but before that we have to find the mass difference or the excess mass or the mass defect or whatever you want to say. Okay, whatever you want to call. Okay, the excess mass or the mass defects. No, defect mass. I'm sorry for that. I'm stupid. The defect mass, right? Defect mass is the mass that you could find from the difference of two things, right? The mass at the beginning, right? I'm not sure which one is bigger, but let's take a look. The mass of radon plus mass of helium-42 or alpha particle. Okay, mass of radon is mass of radon is 222, right? Okay, mass of radon is 222.017 and 571 and plus 4.002602, and you're gonna end up with 226 point I don't know. Okay, it's number 3, is number 7, is number 1, right? In 2 and 7 is going to be 9, and 0 and 1, right? It's number 2 and 0 here. That's the mass of radon and mass of alpha in atomic mass unit. And let's talk about the mass of radon. Mass of radon is here 226.205. So the mass of radium is bigger than the mass of radon plus the mass of alpha particle. So delta M will be the mass of radium minus mass of radon plus mass of alpha, and you will get 226.025 and 402 minus 226.020173. All right, and you just make the calculation. Okay, you get the excess mass in from whatever you get here, right? The energy now we arrive at the energy. Energy will be delta M times 931.5 mega electron volt per atomic mass unit, right? You get a subtraction, the difference here, you multiply with 931.5, and you would get the energy, which is 4.87088135 mega electron volt. Okay, and here is the answer to this problem. Okay, the released energy from this process, okay, the energy you obtain from this process will be 4.8 million. Okay, 4.87 million, and it's quite big, right? It's 4 million bigger than the typical energy you could observe from the electron movement, right? In the EV scale, this is in the mega electron volt scale, right? Okay, now we move to another problem, right? We move to the problem of beryllium. Beryllium, where is that? Beryllium is right here. Beryllium is 84, right? Beryllium is 84 because they have 4 protons. Okay, they have 4 protons and 4 neutrons. Okay, let's get back to this one. Okay, let's talk about the disintegration or the decay of alpha particle in the beryllium nucleus. And let's say atomic mass of beryllium is 8.005305. If you cannot remember, you just get back to this table. You can go back to this table and here. Beryllium is right here. This is beryllium 45. It's not beryllium 884, right? It's another version. but this is an isotope to that beryllium 884. Okay, we cannot use. This is beryllium 94. It's not beryllium 84. Beryllium 84 has no information here. Okay. Yes, but anyway, the problem has provided the useful information, which is the atomic mass of beryllium 84 here, right? Yes, we will compute the, okay, they want to know, this is taken from the book number 1. The previous example is taken from book number 1 too. Okay. This is not a big element at all, right? It starts from only beryllium, which is smaller isotope from beryllium 94. This is beryllium 84. Calculate the release energy when the beryllium 84 splits into 2 alpha particles in what is that? And as according to the typical beta alpha decay rate. From the typical alpha decay. From the typical alpha decay, you have beryllium 84, and you start from Y, the parent nucleus, it's A N Z, right? Is that, and you get, oh sorry, you get X, right? X, which is A minus 4, and Z minus 2, right? And you have here alpha 42. Okay. Once you substitute Y by beryllium 84, right, which is beryllium 8 and 4, okay, you would get any element that has 8 minus 4. 8 minus 4 is number 4, and 4 minus 2 is number 2. Okay, 4 minus 2 is number 2, and X1 we have 2. It's going to be helium, right? It's helium, and on the right side here is also helium. It's alpha particle, right? 42 helium or alpha particle. It's up to you, whatever symbol you want to say, but at least we know that there are 4 nucleons and there are 2 protons, okay, in the nucleus. Whatever symbol, whether you use alpha or helium, He, it's up to you. But it is refers to the same thing. Yes, of course, it's double pieces of alpha particle, and let's talk about the released energy. Before we get the released energy, we compute the mass, right? The excess mass, which is the mass of beryllium minus the mass of helium plus the mass of helium. So we have 2 pieces of the mass of the helium. It's going to be mass of beryllium minus 2 and mass of helium like this. All right. Yes. Mass of helium is somehow this. Mass of beryllium first. That's 8.6. What is that? Oh, here. Okay. Mass of beryllium is 8.005305, and minus 2 mass of helium, right? Mass of helium is the information from the previous problem, which is the 4.002602 atomic mass, and we get something like that, right? Yes, you could get any number, and the way to convert it to the energy is the multiplication by 331.5, right, mega electron volt per atomic mass unit. Okay, it's delta M times 931.5 mega electron volt per atomic mass unit. Okay, you just multiply it, and after you get the difference, the single number here, you multiply 931, you get the result as 4.870 approximately, right? So 813.5. Oh no longer 0.5, and the unit here is mega electron volt. Okay, you get that. That's the released energy from the alpha decay. And now we arrive at the next example. Before that, please let me go to the toilet for a while. ขออนุญาตเข้าห้องน้ำนิดนึงนะครับ Okay. Now we arrive at a more complicated problem, right? Compared to the previous one. Okay, they use the same information, right? Yes. Okay. In this problem, which is taken from the book number 2, it is the extended version to the problem here on page, I don't know, page 47. We are at page 49. Page 49 has the problem which is the extended version, extension to this problem. Okay, they have provided the same information, 4.002602, almost the same number. Okay, you could see here from 2 books, right? the mass of the radium is 226.025.410, but this one is 402. Okay, it's a little bit different, but it's not so significant. It's not so important. Yes, the next thing is the mass of the radon 222.017.017.571 is 578. Okay, a little bit different at the end. And the helium 42 is 4.002603, 4.002602 atomic mass unit here. Right, it's a little bit different, but it's not so significant. Okay, this is the information from two sources, right, from two books, so it might not be the same, but we don't need to pay so much attention to that. All right, just use the principle to compute anything. Show that the alpha emission is energetically possible for radium. What does that mean? It means we have to show whether the radium will bring the energy to this separation. Okay, after the big nucleus is disintegrated to the smaller one like this, you have to determine the whether there is still energy remaining to these two particles or not. Okay, it means they please show that the released energy exists, or the released energy or the liberated energy is greater than 0, is positive, right? If the released energy is positive, we're gonna say this process has the energy, right? Okay, so let's talk about the first question first. We will talk about the second question later after we solve the first one. Okay, this is in the same way as what we have done in the first problem. We need to find the mass difference or the excess mass from the big nucleus, the bigger nucleus, to the summation of these two smaller nuclei. So, two smaller nuclei, and yeah, we find the difference, and after that we convert the mass difference to the liberated energy, and yeah, it's in the same way as in the previous problem, right? Okay, it's my task, right, to show you. Okay, and of course the excess mass first, right? Excess mass, excess mass. Yes, of course, we need to write down it there, right? Delta M will be the mass of radium minus mass of radon plus the mass of alpha particle, right? In mass of radium is this one is 226.025.410, and minus mass of radon is 222.017.578, and plus the mass of helium, which is 4.002603. Okay, everything is in atomic mass unit, and after that you will get the result here. Okay, and then you will find the released energy, right, which is E equal mc squared, but the way for us is only delta M times 931, right? 931.5 mega electron volt per mega electron volt per what is that, per atomic mass unit, right? And the result here is already in atomic mass unit, and after you put it into the calculator, you're gonna have the result like this, which is 4.87, right? Again, 4.87 again, mega electron volt. Okay, 4.87 mega electron volts. And yes, that's the energy you could observe from these, right? You need to find the kinetic energy. The second question is find the kinetic energy of the alpha particle. Okay, alpha particle is the main thing we want to observe, right? So the next thing is the kinetic energy. Kinetic energy of alpha particle. Kinetic energy of the alpha particle. Okay, what is that? We need to know, of course, we start from K alpha, right? Which is 1/2 M alpha. Of course, we know M alpha, and V alpha too, right? V alpha squared. Well, how could we start then? We know that there is no, assume that the radium start from the condition without speed, right? And without speed, the radium would have 0 kinetic energy. Okay, 0 Joule, 0 blah blah blah, right? And but the important thing is there is also momentum involved in this scenario, and we have to take care of that. So the way to solve this one is the following. We know the mass of radon, we know the mass of alpha, right? And yet, of course, from the momentum conservation. Momentum conservation, right? We start from momentum conservation. We're going to solve this from momentum conservation. Okay, the story about alpha decay is gone, right? You know every detail, but we have to get some detail, okay, of the situation after the crash or the separation to this momentum conservation. Of course, this one is the mass of radon, right? It's moved in this way, and this is the alpha particle move in this way, right? V alpha and V radon, right? And of course, this is the vector. From the momentum conservation, the first case and the second case should have the same momentum because we start from 0, the vector 0, right? It's gonna be let's say this is the positive exit, okay, positive x, positive x, okay. And of course, once you move here in this direction, you're gonna have negative M radon and V radon plus mass alpha and V alpha in this way, of course. And you would find that you would have the relation between velocity of the alpha, right? Yes, velocity of the alpha will be you move it to that direction. It's right there. So V radon is negative, right? Of course, if you substitute it in the vector form, you don't have to write down the notation of vector anymore. Okay, V alpha, right? V alpha will be in the this is the magnitude, right? M radon by M alpha times V radon. Okay, that's the amount of the velocity for alpha particle. And of course, you need to divide the kinetic energy to you need to have the conservation of the energy too, right? Okay, they want to find the kinetic energy of the alpha particle. So kinetic moment. What is that? Oh, the summation of this energy, and here you get you get the energy. Because we want to find it. Of course. They found that the momentum would be the same. And of course, yes, from this equation, you get this, right? And from this equation, you could see that this is the 0, right? 0 without vector right now. 0, you have P Rn minus plus P alpha. You see that P alpha equals P radon, right? And yes, of course, kinetic energy is P squared by M, right? So the total energy will be this, right? We're gonna need to transform the energy, the total energy, released energy to kinetic energy, total kinetic energy, right? Yes, the way to do is the following. E will be the kinetic energy of radon plus the kinetic energy of the alpha particle. And of course, the kinetic energy of the radon is going to be P Rn squared divided by M of radon, plus the momentum of alpha square, and momentum square of alpha divided by mass of the alpha square. and you know E, right? That's the value you have got before. And for us is, oh no, there is no M square. We want to find yeah, because a momentum of radon is the same as P alpha, right? So it's going to be P, there should be also 1/2, right? 1/2 here. 1/2 too. Okay, so it's going to be 1/2 and open parenthesis P alpha square plus P alpha square divided by mass of, oh no, you cannot do that because they have a different, because they have a different denominator. So M alpha P square radon plus mass of radon times P alpha square, momentum of the alpha particle. And here you have the common denominator, right, which is mass of N and mass of alpha particle, right? Yes, we go ahead with that. Then we will try to solve this, right? And of course, the momentum of P alpha, P radon will be the same as the momentum of the alpha particle, right? From this relation. And here you could get 1/2 in mass is not the same, right? 1/2 times P alpha square and mass of alpha plus mass of radon divided by mass of radon times mass of alpha. Okay, the summation divided by the product, right? And this is equal to, this is equal to the energy, right? On the left side we have energy. In what else? The important thing is we want to find P squared by M, right? P squared by mass of alpha, right, which is the kinetic energy. Because kinetic energy of alpha is 1/2 P squared alpha divided by mass of alpha. You try to move alpha to the left hand side, you get E equal K of alpha. This is K of alpha. And of course, it's together with mass, right? So this one is mass of alpha plus mass of radon and divided by mass of radon only because mass of alpha has already been changed. We move it to this location, right? So right now, if you want to find K alpha will be mass of radon times the released energy divided by mass of alpha plus mass of radon. Okay, this problem requires a little bit mathematical derivation. Okay, but I hope it's not too difficult to you. You just now substitute, right? The mass of the radon is, okay, kinetic of alpha particle is mass of radon Mass of radon is 226.025.410 divided by 222.0. Oh, no. 222.0175778 and plus the mass of radon, mass of alpha particle, which is the 4.002603. Okay, and here you have to multiply by the energy by caused by the released energy, okay, caused by the excess mass, and that's what we have got before, which is 487, right? You have to multiply 487 mega electron volt, and after that you put it into the calculator, right? You leave this number into the calculator, you get somehow like 4.78. okay, it's nearly 1, right? It's nearly 1, it's not 1, it's less than 1, right? Yes, it's less than 1, so the remaining thing is 4.784, and here is mega electron volt, right? That's the alpha the kinetic energy from alpha particle. But if you don't want something so complicated like that, another way is that, but it's not recommended to do, right? Okay, I would not recommend you to do. Another way is that you just simply substitute the mass number instead of 226 blah blah blah. Another way is you use 222 divided by 226 divided by 222 and plus 4. Okay, simply this one is this one is not 226, it's 222 because it's radon. 222 0 1 7578. okay, and this one is simply 222. okay, if you substitute 222 to this, then you multiply 4.87, it will return a very close value, which is 4.78 and 42, right, which is nearly the same, but this one is 556 in 780604, right, and it's mega electron volt. And that both method give you nearly the same value to the result of this problem. Okay, that's the whole thing for not the whole thing for alpha decay. We will talk about the alpha decay next time. Okay, alpha decay next time. So the time is over right now. We have to finish the lecture at 16, right? We still have 18 minutes more, right? So 20 minutes break for you is ready. So if you have any question, just let me know. Okay, if you are not clear in any detail, just ask me. Okay, if not, then we will finish our lecture today, and tomorrow is the day you have to deliver or submit the linear exam, right? The second time of the midterm exam. And see you on Friday morning. บ๊ายบายครับ สวัสดีครับ